Today, the title of the talk, Chasing the Rainbow. You might get some hints about what the topic is there, especially if you read. First of all, this is not an ad for Skittles. Chasing rainbows, if you look, the reason I chose this talk, if you look it up, it means pursuing things that are unrealistic or unlikely. Chase, another important word here, to follow rapidly, to catch or overtake. If you want to catch something, if you're chasing it, you have to know where it's going or you're never going to catch it. Rainbows, actually, they're spectral power distribution that's spread out in space. It's a path, we can follow it. If you follow this one, that actually happens to go to my neighbor's house right there. They really love this picture. They have it inside their house. But legends tell us there's a pot of gold at the end of the rainbow. So that has something to do with why we're talking here today. Lighting parameters. We were talking about flux. You have luminous flux, photon flux, radiant flux. Right now you can predict luminous flux based on TM21. If we're lucky in a few months, the revision to TM21 will let you predict photon flux or radiant flux. Chromaticity, we have XY, you can do U prime, V prime. You can calculate the change in chromaticity, hopefully TM35, again later this year. CCT, DUV. SP ratio, for those of you who are doing street lights, work at night. Color rendering, color quality, we have CRI, R9 people worry about. TM30, you have RF and RG. Photobiology, right now we have IEC 62471, so this is your photobiological hazard. At some point we're going to have a circadian metric. This is our pot of gold. This is everything we get from the spectral power distribution. These are dependent variables. We really only have one independent measurement. Unfortunately, right now we throw it away. Reliability standards, obviously they predict the parameters. If you look at the development process, if you guys really want to do this, please join the IES Test Procedures Committee. We can use a lot of bodies for this. It takes a lot of time and effort. So we define a parameter. This might take 2 or 3 years of discussion. How do you actually calculate the parameter? Once people know how to do it, usually it's out in the literature, people are talking about, but you get a group of experts together. We spend about as much time saying, this is the standard, this is the official way to calculate it. We've known the general way to calculate it, but this is how you're going to do it exactly. Then we start collecting data. We need 3 to 5 years of data collection. Why do we need that long? 3 years is 25,000 hours, okay? If you want to predict, if you want to know that your predictive model is good and it's accurate, you have to be able to compare it to real data out in time. So we need between 25 and about 40,000 hours of data to be able to say, hey, this model really works. After that, we might be able to predict it because there's a chance we go through all this effort trying to predict it, testing the model versus the actual data later in time, and it might not work. So why don't we just calculate everything from the SPD? That's where we get all the parameters anyway. If you look at lumen maintenance, TM21, that's one parameter versus time. Sounds like it's easy to do. Chromaticity shift, we're actually predicting 2 parameters versus time, U prime and V prime. Doesn't seem too bad, we only added 1 more. If you look at a white LED, typically it's an LED and a phosphor, maybe 2 phosphors. So can't we just model each emitter? Sounds like a great idea. There are a couple papers out in the literature that do this because it's only a phosphor or 2. It doesn't really sound that bad. Here's the reality check. For a reasonably accurate model, we need at least 20 parameters. You also have to know something about the package of the LED to prevent mode hopping, which I'll explain in just a minute. And the short summary is it's really complicated, even if you know the details. Mode hopping, this gives you an idea. So this is an actual spectral power distribution. All these dashed lines, you can see what you can't tell. There's a red and blue. This looks purple. So that's the model. All these dashed lines, including this one that goes down below, work out to what the spectral power distribution is. Anyone have an idea why this goes negative? The phosphors have to absorb the light. Each one of these, you've got a center wavelength. They're not symmetric, so I've got what's the spread, what's the half width, half max on this side What's the half width, half max on this side? What's the intensity? So each one of those peaks has 4 parameters, okay? I've got 5 in here. That's my 20 parameters. What happens with mode hopping is if you try to automate how to fit all these, sometimes when it changes over time, this peak over here might all of a sudden hop to the other side. So if you look at that center wavelength over time, it might jump dramatically. Here it's decreasing, here it's increasing. This is why you have to know the details before you try this method. And if you want to talk to LED manufacturers and say, tell me everything you're using in your package, it's not a problem. You can ask them that, and you can wait and wait and wait, and I doubt you will get the answer, but they might tell you they're using a blue LED chip. An alternative approach. The real thing is only we had experience with a light source that changed its spectral power distribution over time in a predictable manner. This would make life a lot easier for us. We do. This is the 20th anniversary. We've been talking about history, so actually went back to history. If you know about D-series illuminants, they're actually calculated. There are 3 what they call eigenspectra, and it's a linear combination. The trick is, these 2 parameters, M1 and M2, they're a function of correlated color temperature, so you pick it and you can calculate it. So what I'm asking you is, do you think a similar approach will work for LEDs? Obviously, since I'm talking here, it will do something. So TM21 is the standard people are most familiar with. It assumes lumen maintenance is an exponential decay in time. So we take all these hours. I happen to have some nice data sets that go out to 14,000 hours. And I'm using this equation. So I have this I'm calling the first eigenspectra. This is the second one. And this is the closest analog to what we do for lumen maintenance. Okay. So the purple, this is what it is at 1,000 hour. And if you look at the blue and the red, that's the actual data versus the prediction. If it looks like it's really close, it is. Here you go, here's your predictions. Turns out this is actually more accurate than TM21. I've only gone from 6,000 hours to 14,000 hours. TM21's off by almost 3.5%. Chromaticity shift. TM35, if you know how the calculations are right now, which fortunately I do, it's a little more accurate than that too, because we're calculating from the spectral power distribution. We're not using the dependent variables, we're using the independent. What else? What else? Radiant flux, about 1% error, not too bad. Photon flux, again, about 1% error, not too bad. I can actually break this down into different wavelength bands. If there's anyone here who does horticulture, if you want to know UV, blue, green, red, far red, I can give you all those numbers as well. And the error is about the same. SP ratio, pretty good prediction. CCT, here's one you usually don't see. Can you predict CCT over time? 31 Kelvin, over 8,000 hours, I don't think is too bad. DUV, where you are above or below the black body locus, again, pretty darn good there. Lucas, swell factors, lighting designers. So all of these, look at these errors. We're actually predicting these parameters versus time. These are brand new things. The well standard has not been out that long. Color rendering, not just RA, every single value. You want to predict your R9? Go ahead. TM30 even works for that. Down to your graphics. So if you want to look at color distortion or the color vector graphic, you can predict these in time. If you want to do the eigenspectral analysis, the first eigenspectrum is boring. This is your spectrum at time 0. It doesn't really have any useful information. The second one starts getting a lot more interesting. Now this is your rate of change versus time is basically what we're looking at here. You see this feature. Does anyone have an idea what that means is happening? Anyone? Wavelength shift, that's a peak that's moving in time, exactly right. What do you think this is? Something's decreasing. What's decreasing? As a matter of fact, it is about a 95, 96% match to a commercial phosphor. I can tell you in this particular case, the red phosphor is dying. This shows up, it's because of the change in the excitation spectrum. Since the phosphor is dying, it's not absorbing light quite the same, so it's shifting over. So I knew nothing about the package until I did this. Honestly, when I started this work, I only expected to predict the parameters. When I looked at this, I scratched my head and I said, wait a minute, now I know something about how the package is made, and all I needed was the spectral power distribution. In terms of analysis, even if you know what's going on, this can tell you the details, and you haven't had to pick it apart. So if anyone's had to section a package, extract phosphors, run through Auger analysis, try to figure out what's going on with your phosphors, this gives you a lot better idea. You know exactly where to look. So, perspective, even this simplest implementation of an eigenspectral analysis gives us accuracy that's comparable to the standards we use now, except we're predicting the entire spectral power distribution. If this can be developed as a standard, this is probably the only reliability model we will need related to light output, because everything comes from the spectral power distribution. The extra bonus here is the eigenspectra themselves give us valuable information about the aging. It can tell you exactly what's going on, or at least point you in the right direction and help you make a better package. Takeaways. This has been a theme of mine with Sub-S inside the Test Procedures Committee. We've been reactive in the past. We've waited for the industry to ask for things. We waited for metrics to be developed. If we want to be proactive, well, actually we can't with this. We have to wait for people to tell us. Okay, if we want to be proactive, then we want to be ready as soon as things are available. Part of this Nancy brought up in this morning's keynote about the spectral power distribution. The standards are being changed to require saving the spectral power distribution for the customers. A new metric comes along, calculate it. We have the spectral power distribution. Don't go start measuring it again. Just do it from the historical data. And the nice bonus, a willingness to embrace ambitious goals, which chasing rainbows is. Sometimes it pays dividends far in excess of what we expected. Like I said, I only expected to be able to predict parameters. I didn't expect I would be able to give people information about what's happening in their packages and give them hints on how to make a better package, a more reliable package, or make changes for some of the parameters that our customers would like. That's it. Any questions?
What was the resolution you wanted for the spectral power distribution?
This is 1 nanometer intervals. No, it's not, but when people are measuring LEDs, they're using a spectrometer, they're doing a spectroradiometer to be more technical. They're calculating the luminous flux from that, and then they're normalizing it. So the information's there, they just calculate a few parameters and throw it away. And for those of you who want to know why we didn't do it in the past, memory used to be expensive. A single terabyte, which I can buy for about $50, will let me save 1 spectral power distribution a second for about 3 years. So it's not a cost burden.
Is there any other questions from the audience? Well, good, I get to ask a question. So how many different types of package architectures have you validated with your methodology?
The full data set includes about 60 sets of spectral power distributions.
And are they typically on the same type of package, like a high power, or is it a
high power, mid power, EMC, and the high power is both ceramic. Most of them are ceramic, but some of them are other alternatives. It's a good representation. The problem is 14,000 hours is a tease. 25,000 hours, I could really start saying things. 35 or 40,000 hours, we'd already have a PIF and be working on this.
Yeah, and those are older style packages that are getting to those, getting on those lifetimes. So.
Yes.
Question over here.
Can it come across any situation where we need a second rate competition?
Not yet, but I'm not going very far in time. I'm expecting that probably 3, maybe 4 Spectra will handle everything, but it's limited data, so that's what you're seeing. I thought I might need an extra one, do a total of 3, but so far 2 works just fine.